Previously, we have pointed out a serious problem with our tentative definition of intersection number. The problem is that under this definition, homotopic maps do not necessarily have the same intersection number. For example, in this picture here, this map F0 and F1 are homotopic, but the intersection number of F0 with Z is 4, whereas the intersection number of F1 with Z is just 2. Recall that we said there are two ways to fix this. One way is to only define the intersection number up to modulo 2, because these two intersection numbers will always differ by an even number. And then the second way to fix it is by assigning orientation and count the intersection numbers with orientation. In this video, let us discuss intersection theory modulo 2. Alright, so let's define this formally. Again, the setup is that we have an embedded submanifold Z of submanifold N, and then we have a map F from M to N. Here we assume that the M and Z are of complementary dimension, and that M is compact, so that this intersection number is going to be finite. Now, if F is transversal to Z, then we define the intersection number between F and Z to be the number of points in this preimage, modulo 2. So now we add the condition that this is modulo 2. So this intersection number is an element of Z mod 2Z. Alright, so that's if F is transversal to Z. What if F is not transversal to Z? Well, then as before, we deform F, i.e. we find a map G homotopic to F such that G is transversal to Z. And then we define the intersection number of F with Z to be the intersection number of G with Z. Now let's check that this definition resolves our issue. In other words, let's show that homotopic maps have the same intersection numbers modulo 2. For that, we will need the classification of one-manifolds. So let us make a little digression and talk about this. We have the following theorem. If M is a compact connected manifold of dimension 1 with boundary, then there are just two possibilities for M up to diffeomorphism. M is either going to be diffeomorphic to the unit circle, or it's going to be diffeomorphic to this unit interval. We can see that intuitively as follows. So if we start from some point in M, then there's just one dimension. So there are just two directions to choose from. So let's pick one direction and keep going. Because M is connected, so we're never going to leave the connected component. Now because M is compact, so we cannot run forever. Thus there are two possibilities. Either we come back to the point that we started with, or we reach an endpoint. We can repeat the same thing in the other direction. Either we'll come back to the original point, or we reach some endpoint. So one-dimensional compact connected manifold with boundary must be either diffeomorphic to the circle or the unit interval. Now that's the case if M is connected. In general, if M is just a compact manifold with boundary of dimension 1, then it's going to be a union of circles and unit intervals. So in particular, we have the following seemingly trivial corollary, which is that the boundary of any compact manifold with boundary of dimension 1 must have an even number of points. This seemingly trivial fact is actually very useful. It will allow us to prove a few important theorems. For example, we can use this simple fact to prove the following well-known theorem from algebraic topology, which says that there is no retraction from the closed unit ball to its boundary sphere. Or more generally, there's no retraction from a compact manifold with boundary to its boundary. And then, as with the case in algebraic topology, we can use that theorem to prove Brouwer fixed point theorem. But we won't do that now because we don't want to digress too much. So let us just prove this. Usually in algebraic topology, we can prove that there's no retraction of the closedest to the boundary sphere, just using the functoriality of the fundamental group functor. But now we'll try a different approach. Recall that a retraction here in this case is a smooth map from X to its boundary such that this map restricts to the identity on the boundary. i.e. every point on the boundary stay fixed under this map. Alright, so how would we prove this? We'll prove by contradiction, so we'll assume that there is such a retraction R, and then we'll take a point P in the boundary that is a regular value of this map R. Well, such a P must exist because of Sartre's theorem. Now let us consider the fiber over P. Right, so these are all the points that retracts to P. Now we claim that this fiber is going to be a compact, one-dimensional manifold with boundary, which will allow us then to use this classification on this fiber. Well, this comes from the transversality theorem for manifolds with boundary. Let's review this. Let's say we have a map F here that is smooth and transversal to this submanifold of this manifold N. Recall that when M is a manifold without boundary, then all we could say was that the preimage of Z is going to be a regular submanifold of M. If M is a manifold with boundary, then we have more things to say. So then in that case, this preimage of Z is going to be a manifold with boundary. We have a description for its boundary, and we have that the codimension of this preimage inside M is going to be equal to the codimension of Z inside N. In particular, this last statement here means that the codimension of this preimage inside X is equal to the codimension of P in this boundary. But dimension of P is just 0, so this codimension is really just equal to the dimension of the boundary, and that's just equal to the dimension of X minus 1. So if the codimension of this preimage is equal to dimension of X minus 1, then that means that the dimension of the preimage itself must be 1. So from this we see that this preimage must be a compact manifold with boundary of dimension 1. Now let's see what its boundary is. From this statement we see that the boundary of the preimage should be the intersection of the preimage with the boundary of this manifold. So the picture should look more like this, right? The boundary of this preimage has to lie on the boundary of the manifold. But note that it can't really look like this because this point is gonna map to itself. It's not gonna map to P because the map is identity on the boundary, right? So this cannot lie in the fiber over P. So since all boundary point of this preimage must lie in this boundary, right? But they must also retract to P, the only possible boundary point for this preimage is P. But then this preimage has only one boundary point that contradicts the fact that every compact one-dimensional manifold with boundary has an even number of boundary points. So that's a contradiction. And thus there cannot be any retraction from a compact manifold with boundary to its boundary. Alright, so we have digressed a lot. Remember, why did we want to talk about this classification of one manifold? That is because we want to use that to prove that homotopic maps have the same intersection number modulo 2. And we'll do that in the next video.